Welcome to Measurement Study of a Process, Lesson 3. In Lesson 2, we looked at process variation and common causes of variation, statistics, including how to calculate range, mean, median and mode. We learned more about the normal distribution curve under the effect of location and what a skewed distribution curve looks like. In this lesson, we will look at how statistics can be used to tell us how well a process is under control. As we have now learned, to determine if a process is under control, parts need to be measured during the process. We have looked at statistics, including range, mean, median and mode, and learned about variation in a process. We will now look at statistical process control. This is a control system which uses statistical techniques for knowing, all the time, changes in the process. It is an effective method in preventing defects and helps continuous quality improvement. It is abbreviated to S.P.C. Let's look at each S, P and C on the next slides. Statistical. Statistics are tools used to make predictions on performance. There are a number of simple methods for analysing data and, if applied correctly, can lead to predictions with a high degree of accuracy. Process. The process involves people, machines, materials, methods, management and environment working together to produce an output, such as an end product. Control. Controlling a process is guiding it and comparing actual performance against a specification. Then identifying when and what corrective action is necessary to achieve the specification. Part of these lessons is to understand how we determine if a process is statistically capable. Statistics aid in making decisions about a process based on sample data, and the results predict the process as a whole. So, we need to collect data. Statistical process control concerns the use of statistical techniques to help achieve one or more of the following objectives: to increase knowledge about a process, to steer a process to behave in the desired way, to reduce variation in a product, or in other ways improve performance of a process. Detection. This focuses on identification of problems after production by 100% inspection, sampling, or by customer complaints. It is a historically based strategy. Remember our 50 parts that we measured? We detected the 2 parts that were out of tolerance after they had been produced. Detection drawbacks. Production is already made. Customer dissatisfaction. Inflated costs, rework, inspection. Repetitive problems. Neglected improvements. Prevention. This focuses on in-process production and identification of problems through analysis of process capability. It is a future-orientated strategy. Prevention benefits: improved design and process capability, improved manufacturing quality, improved organization, continuous improvement. S.P.C has to be looked at as a stage towards completely preventing defects. With stable processes, the cost of inspection and defects are significantly reduced. We have looked at some statistics including range. Although the range is an easy way to measure variation, it has a drawback. The range only takes into account the extreme values and disregards all other information. To overcome this, standard deviation is used as the preferred method of spread. Standard deviation is a measure which reflects variability and dispersion of a process. The greater the variability, the greater the standard deviation. Standard deviation is represented by the symbol sigma. Standard deviation for a sample is calculated by the following formula. Here we can see sigma is equal to the standard deviation, x equals each value in the sample, x bar is equal to the mean average of the values, and n is equal to the number of the values. So, calculate the mean, then for each number subtract the mean, then find the sum of those squared results, divide that result by the number of samples minus 1, then find the square root of everything. Don't worry about doing the calculation on the previous slide, as calculators and spreadsheets can do this for you. Let's compare 3 sets of sample values. And here we can see 3 graphs showing 3 sets of sample values. But there is something interesting. The range, the sum of x, the number of samples, and x bar all have the same set of values for each chart. However, here we can see the standard deviation is different for each set of sample values. As we have already seen, the distribution most frequently encountered in industrial processes is the normal distribution. This is important because knowledge of its properties enable us to make predictions about machine and process performance. So why do we need to know about standard deviation, or sigma? Process capability is determined by a comparison of process performance versus specification. Process capability depends on specification limits, depends on the process spread, i.e. the standard deviation, sigma, depends on the process average, and can be described by a capability index. Capability is a measure of the ability of a process to meet specified requirements, usually expressed as an index CP. The process capability index can be made using a formula. CP is equal to the tolerance divided by 6 standard deviations, or 6 sigma. The capability assessment compares the process spread with the specified requirements. We already have 50 measured parts, so as we know the tolerance and we can calculate the standard deviation, we should be able to calculate our process capability index. So get out your calculators and let's see your result. Process capability is equal to the tolerance divided by 6 standard deviations. So our process capability is equal to 36.37 minus 36.27, which was our top and bottom tolerance for our bore diameter, divided by 6 standard deviations. So our process capability is equal to 0.1 divided by 6 times 0.014058. So I worked out sigma for you. So our process capability is equal to 0.1 divided by 0.084348. So our process capability is equal to 1.185. So our CP was 1.185. But what does that mean? If the value of CP is less than 1, the process variation is greater than the specified tolerance. The process is therefore not capable of meeting specifications. Such a process will always produce some parts that do not meet specifications. If the value of CP equals 1, process variation equals the specified tolerance. The process is barely capable of meeting specifications. If the value of CP is sufficiently greater than 1, process variation is smaller than the specified tolerance. The process is capable of meeting specifications. In this case, the chances of producing non-conforming parts is very low. This is the most desirable situation. As we have already seen, the distribution of our data shows that it fits a bell curve, so the distribution is considered normal. We also understand that the CP has to be sufficiently greater than 1 for a process to be capable of meeting specifications. Industry guidelines suggest that CP should be greater than 1.33 for a process to be considered capable. So, does our CP of 1.185 mean that we have a capable process? We already know that from our 50 parts, 2 parts were outside of tolerance. We have now statistically proven that our CP value is not sufficiently greater than 1. So it is no surprise that the process used to manufacture those 50 parts was not a capable process. In our 4th and final lesson, we will learn more about process capability and learn that our process can be controlled as it happens using an example of a process control chart.